So we've been talking about the derivative, and just as a reminder, what is it? It's the function, the derivative of the function f of x with respect to the variable x is the function f prime whose value at x is this difference quotient, provided the limit exists. So again, you have all those small caveats. It's a function, the limit exists, we're talking about this with respect to the variable x, so if it's a multivariable function, again, don't worry about that unless you're in Calc 3. It has to correspond to which way that it's changing. So this is how we've been finding functions and their derivatives, or the derivatives of functions. Because if I give you this, so x to the 7th minus 13x to the 4th plus 18x cubed minus 5, and you sit here and decide, or not decide, but if I tell you this is what you have to do, I can go and take a nap, and by the time you've multiplied out x plus h to the 7th, I might be starting to wake up. At some point, it becomes completely inefficient and completely unreasonable to keep using the difference quotient. Difference quotient is great for proving, but it's not the most useful tool like in this case. So what if we can kind of come up with some rules that work in general for functions? Because if you want to do this, nobody wants to do this. But if you had to do this, it's just going to take a long time. So let's kind of start to establish some of these rules. So think of a function that's just a value that's a constant. So like f of x is 7. So it doesn't matter if I plug in 1. It doesn't matter if I plug in negative 17, 32, 40, whatever. It's always going to be that constant value. And so the derivative of a constant is 0. Because remember, this is the instant rate of change. If it's a flat line, then there is 0 slope at every point on the line. Because even if you do the difference quotient, the problem is when you do f of x plus h minus f of x, if it's constant, then it doesn't matter if it's x plus h. I have the limit as h goes to 0 of c minus c divided by h. So constant makes sense. It's just never going to have kind of a reasonable value or a useful one. So, and it doesn't matter the constant. If it's pi, 17, square root of 3, negative 14, whatever, derivative of a constant is always 0. So even if you have weird ones like e to the pi or like square root of 2 raised to the 15th power, that's still the derivative of that constant is always 0 because it just doesn't change. And these are the rules that you want to kind of start boxing, start memorizing, because these are very useful and they'll save us a lot of time. And then probably the most useful and probably the most used rule in calculus. The derivative of x to a power is multiply that power out front and then subtract 1 from the exponent. And you may have started to notice this pattern beforehand. Like when we would do x squareds, they would come out to be 2x. When we did 4x squared, I think it was 4x squared on the test, that came out to be 2x, which is just 2 times the 2x. I never had y'all do an x cubed, but if you had done x cubed, you would have got 3x squared. and so on and so forth. So it doesn't matter regardless of the value, as long as it's x to some power. Because even though that I've got here, it's a positive integer, we can actually kind of relax that. And remember I said that the limits were this linear idea, that I could split a limit over two things. So if I had the limit of the sum, that was the same as the sum of the limits. We said that it was a limit, that constants could just be pulled out to the front for limits. And since the derivative is based purely on the idea of limits, it makes sense. Because if I had c times f prime of x, or let's use f prime of x just for example. We'll say that f of x is equal to we'll do c times g of x. So then f prime of x is equal to the limit as h goes to 0 of c times g of x plus h minus c times g of x all divided by h. Well, then I could factor out c to the front, and so that would leave me c times the limit as h goes to 0 of g of x plus h minus g of x all divided by h. But that's just the definition of the derivative for g of x. So you're just using the difference quotient and its definition to kind of get these rules. So again, for this one, I forget what it was on one of the tests, but we had like f of x, I think it may have been a practice problem. We had like f of x is equal to 2x squared, I think plus 1 or minus something. But so if I want to do the derivative of this, let me do this next rule first. Derivatives are made up of limits. Limits can split over a sum. So thus a derivative should be able to do the same thing. So if I have the derivative with respect to x of f plus g, what we say here is the derivative of the sum is the same as the sum of the derivatives. Because here's the derivative of a sum, and here's the sum of the individual derivatives. And you just you follow the rules, but you have to split them over. So again, most commonly used one is this x to some power. So I'm just going to do that individually for each one. You bring down the 7, subtract 1, get 7x to the 6th. You bring down the 5, subtract 1, get 5x to the 4th. So if we wanted to do this one, sorry, the derivative of 2x squared plus 1, then all I'm doing is, you can almost think about the derivative as kind of like being distributed over a sum. The same way as if you had like 3 times this, you would distribute it. Derivative gets done that way. But since it's a constant, instead of doing the derivative of 2x squared, I can just do 2 times the derivative with respect to x. This part down here is where that with respect to x comes from. Of x squared plus the derivative with respect to x of 1. Now the problem is you can't move the 1 out front because it's the only thing there. So then 2 gets left alone because it's a constant. Derivative of x squared, you bring down the 2 and subtract 1. And then 1 is a constant, so it dies and goes to 0. So this is equal to 4x. Now, whenever you're doing the derivatives, because typically the question comes, so do you want us to write all these steps out on a test? You don't have to do all these steps. If you say, okay, I'm taking the derivative, and you go from here to here, if y'all are sitting here, I know that you have the ability to do that. It's not one of those things where writing all those steps down is necessary. If you understand the process, you're going to get to this. That example popped up way too late. So part of the reason that this is useful, remember when we did the square root of x? Remember how much of a pain in the butt that was to multiply by the conjugate, go through all the algebra and everything, just to get 1 over the square root of 2. Or 1 over 2 square roots of 2. If I want to do the derivative of the square root of x, what's a way to rewrite the square root of x? X to the 1/2. And this is why that's useful. I've now rewritten this as x to some power. So I'll bring down the 1/2, and then I'll have x to the 1/2 minus 1. So that'll give me 1/2 times x to the negative 1/2. And remember, a negative exponent, all it does is if it's in the numerator, moves to the denominator. If it's in the denominator, it moves to the numerator. So this is going to move this from the numerator into the denominator. And then we can just rewrite this as 1 over 2 square roots of x. And we didn't have to write out the difference quotient. We didn't have to multiply by the conjugate. We didn't have to do a bunch of algebra to keep up with. And it's all because this x to the nth power rule can be applied to x to, well, any power really. So any questions on any of these 3 rules so far?
How did you determine D?
Which part?
How do you determine D?
Up here?
Yeah.
D is just the shorthand for derivative. So you kind of have to, you read it kind of weird. It's like the derivative of f with respect to x. So it's kind of like df is like the derivative of f, and then the bottom dx is telling you what derivative you take the what you take the derivative with respect to.
So how'd you get the 2x in the first one?
For here,
Yeah.
so first thing I did was, if I'm going to take the derivative of this, I don't want to try and take it all as one big chunk to start out with. Later on, as you get more comfortable with them, you can just look at it and immediately know it's 4x. But so this would be the derivative of 2x squared plus the derivative of 1. Both of them are with respect to x. But I'm using this rule here. So instead of having this first part where I have like the derivative with respect to x of 2x squared plus derivative with respect to x of 1. Because the thing is, my rule is I know the derivative of x to a power. I don't necessarily know the derivative of something times x to a power. But the thing that I'm multiplying by is a constant. So I'm going to apply this rule here to kind of move and push the constant out front. So then once I'm here, this is the derivative of x to a power. So that becomes 2x. Leave the 2 alone. Derivative of a constant, this term dies and goes to 0. And so then it's just a matter of multiplying it out. Because one thing I'll say is this is kind of, I won't say it's bad notation, but you have to think about like d and dx. Right now, you think about it as one unit, where d is working as the derivative, and dx is telling you what variable to do that derivative with respect to. Later, we'll do what's called implicit differentiation, and that's when that with respect to part becomes very, very important. Also, once we get to something called chain rule, it's extremely important there as well.
So basically, that bottom x, it could be a c, a b, whatever, and it just means that's what you're looking for.
Yep. Like if your function was in time, like maybe like the gravity problem we had last class, then you would just do d dt.
So it's kind of just like a placeholder.
Exactly. It's just telling you this is the variable that you're looking for the rate of change of. Because the thing would be if my function was like an f of y, then asking what's the derivative with respect to x for the function y is kind of silly, because it's like there's not an x in it, it's all y, so you have to be careful about some stuff like that. So these are kind of the 4 basic rules to start out with. X to a power, bring down the power, subtract 1. If there's a constant, and this doesn't just apply to x to a power. Once we get into some of the other derivatives, constants, you just kick them out to the front and don't worry about them until later. And then some just derivative of individual terms. And then the previous slide, derivative of a constant goes to 0. So those first 4, straightforward. Unfortunately, I'm getting ahead of myself. I know where this is going, and I'm getting too excited about where we're going for it. But the nice thing is now you can find the derivative of any polynomial. So if you ever see differentiate, what's the instantaneous rate of change? Those are all asking for derivatives. So what would be the derivative of this function? 3x squared minus 7. Bring down the 3, subtract 1. Now, if you look at this and go, okay, well, why isn't there an x there? This is the derivative with respect to x of x to the first power. So we bring down the 1, and then multiply by x to the 1 minus 1. So that gets me 1 times x to the 0. If it's to the 0 power, it's 1. So the negative 7 got left alone, and then the derivative of x just kind of disappeared. A kind of not necessarily bad way to think about it, but sometimes for explaining it, this becomes the rate of change of x over the rate of change of x, which would also make sense why it becomes 1, because it's dx dx. You have to think about these as whole units. The thing is, like, you can't just cancel out parts of these, because like this is equal to 2x. The d that's at the top is an operator acting on the whole function. The dx in the bottom, or dt, dy, whatever, that's an operator acting on what variable you're taking the derivative with respect to. So then what would be this derivative? Negative 2x plus 6. So negative, you can think about that as a negative 1. So just ignore it and push it out to the front. This becomes negative 2x because we bring down the 2, subtract 1, plus 6x. Same thing applies up here. This becomes x to the 0. So 6 gets left alone. Derivative of a constant goes to 0, so that term dies and we just don't have it anymore. A little bit trickier. But at the same time, it's not that much trickier. What would this derivative be? Yep, 2x minus 0.5512. Constants, regardless of how they look, are always still going to be treated the same way. Pi over 2 is a constant, so its derivative is 0. 0.5512, it's a constant, so we just leave it alone when we do that derivative. What about this one?
81x to the 8 plus 36 to the 5th, and then 9 to the 2nd.
Because this would be 9, and then 9 times x to the 9 minus 1, plus 6 times 6x to the 6 minus 1, plus 3 times 3x to the 3, not minus 2. Three minus 1. And then you can think plus 0. So with these rules, it makes it a lot simpler to do this. Again, you look at that very first one we did, that you'd probably still be multiplying out the x plus h to the 7th part right now. And now we know this would be 7x to the 7 minus 1. Leave the 13 alone. Get 4x to the 4 minus 1. Leave the 18 alone. Just do the derivative of x cubed and get 3x to the 3 minus 1. And derivative of negative 5 is just 0. So we'd have 7x to the 6th minus 52x cubed plus 54x squared. You didn't have to do a bunch of multiplication. The worst multiplication you had to do was like 13 times 4 and 18 times 3. But sure as heck beats doing the difference quotient on x plus h to the 7th. So any questions on any of those? So, like I said, these you want to be familiar with because these rules are pretty much going to be what we have to use and are going to use for the rest of the class. So now we can kind of ask the same questions we've done before. So where are the horizontal tangents of this function? So what does it mean to ask where is a horizontal tangent? So the tangent line determined the slope, right? So if I'm saying it's horizontal, that means it's completely flat. And so if it's completely flat, what I'm really asking is, I want to know where does the derivative equal 0? So horizontal tangent and where the derivative equals 0 are interchangeable. Same thing, different name. So if we take our derivative, this will just be 4x to the 3rd minus 4x. And you want to set that equal to 0. The nice thing is we can factor this out. There's a 4x that's common amongst everything. So that leaves me 4x times x squared minus 1. X squared minus 1 is the difference of squares. So I have 4x times x plus 1 times x minus 1 is equal to 0. And so remember, nice thing about polynomials is you can just set the individual terms equal to 0 and figure out the roots of it. Because if they're all multiplied like this, then I know the derivative is 0 at -1, 0 and +1. And if we look at the graph, that lines up exactly. Any place the graph went from increasing to decreasing or decreasing to increasing, the derivative was 0. Now, again, sometimes you can have it where it goes from increasing to increasing or decreasing to decreasing. We just kind of have, that's still an interval of decreasing, but it just kind of takes like a pit stop at one point. And again, this did not ask what is the equation of the tangent line where the horizontal tangents occur. It just said, where do they occur? So when I've said before, don't get the right answer to the wrong problem, this is one where you could go and do way more work than you have to, where you find the tangent lines. So you don't want to do too much work, you don't want to do too little work. So just always be aware of what it's asking. Now, the product rule is where things get a little bit trickier. This is what I was alluding to earlier. Derivatives work when it's over a sum or a difference, like if you had a constant that you were multiplying. So if you had like x squared plus 5, so let's say you had like x squared plus 5 and you multiplied it by 3. Then you know you have 3x squared plus 3 times 5. But if you have 3 times, let's say x squared times 5, then there's an issue. It's not equal to 3 times x squared times 3 times 5. Derivatives are the same way. They don't just get distributed in. One of the most common starting mistakes is having two things multiplied together and just taking the derivative of them individually. This proof, the reason I can do like the quick proofs for like adding two things, the constant one, is they don't take about a page to do. This one has one of the most clever uses of adding 0. And what I mean by that is there's a specific thing that you can add into this that doesn't change it because you're just adding 0. You change the way it looks, and then you get this nifty thing. But everybody kind of has like a similar way of remembering this. My shorthand is it's the first times the derivative of the second plus the second times the derivative of the first. So if you like to have it in words better, that's kind of the way to go about it. So if we had this first one, we want to do the derivative of x to the fourth plus 5x squared times x cubed minus x. So you could multiply this out. You could multiply it out, get a polynomial, and then work with it from there. That's completely acceptable. There's nothing wrong with that. Later on, though, we'll get to functions that you can't multiply out. Like if you think about like trig functions or like square roots and stuff like that, you're not going to be able just to multiply those in and kind of clean things up nicer. It might actually make things messier to deal with. So first things first, whenever you come to one of these where it's a product, you just want to establish which pieces are which. So I'm going to call this first group of parentheses, this is going to be my f function. And the green part here is going to be my g function.
But you get to choose it, doesn't matter if you use after G.
Correct. I'm just lazy and I go first one, second one. There is a general product rule that expands out to like if you have n terms. Basically what ends up happening is like you have an f and a g and an h. You kind of just like go, okay, well here's first and second times derivative of the third plus first and third times the derivative of the second. You basically just like move down the list to make sure you get the derivative of each one. Don't have to use that one too much though. But yeah, the nice thing about this one, you could swap the order if it was easier. But so when I do this, I want the first times the derivative of the second. So I'm just going to rewrite x to the fourth plus 5x squared. So that's my f of x. But then I need to multiply this by the derivative of the second term. So what's the derivative of x cubed minus x? 3x squared minus 1. So we have first times the derivative of the second. So now I need just the second, so I'm going to rewrite it this way. So x cubed minus x. And then what's the derivative of f of x? 4x cubed plus 10x. Yep. And so the thing is, it doesn't necessarily matter the order with these because they're multiplication. You could have written it as first times the derivative of the second plus derivative of the first times the second and kept the orders a little different. The main reason that I choose to do it this way is kind of the symmetry here kind of helps me keep it straight as to what needs to go where. So f times g prime plus g times f prime, like I can close my eyes and I can see it that way. But product rule, I'll just go ahead and say, this is one of the most common mistakes people make is just seeing like this and doing 4x cubed plus 10x and then saying that's times 3x squared minus 1. Most common mistake that will happen where people know the power rules, the sum rules, but as soon as you multiply stuff together, things get clogged up as to what needs to go where. So, any questions about the power rule? Or not power rule, product rule. Had some of the correct letters. Now, if there's a product rule, there needs to be a quotient rule. And the quotient rule, like before, you said you can just kind of pick which one's F, which one's G, and it doesn't make a difference. This one, order is crucial. And I did not have a nice way to remember this. One of my friends in grad school told me the way that he remembers it, and once he said it, it finally clicked. I had got to the point where sometimes I would have to rederive the quotient rule using other rules just because it made more sense that way in my head. But if you think about this one as your high function, so the numerator, and this is your low function. This is low d high minus high d low, and then square what's below. So low d high minus high d low and square what's below. And it's so stupidly catchy that I can't forget it, and I'm very upset that I did not learn that way to remember it until grad school. Because it's basically just summarizing what this is. Denominator times the derivative of the numerator minus numerator times the derivative of the denominator all over the denominator squared. And again, part of the reason I tend to use the same order, notice I have g, and then this would be like f prime minus fg prime. I have a similar bit of symmetry going on there. Not the same, but it helps me kind of keep straight in my head how they need to go. So if I want h prime of x, I just need to go over to this. So it's low, so I rewrite the denominator. So x minus 1. So that's my low. D high, so d just is a stand-in instead of saying derivative. So what's the derivative of the numerator? 6x squared. And then minus high, which is 2x cubed, times what's the derivative of the denominator? Yep, just 1. And then we just square what's below, so then that's just x minus 1 squared. Now, I'm not picky about like multiply your like terms, put everything together, this, that, and whatnot. Some of the questions they even have like just take the derivative, you don't need to simplify. This is one of those where you don't need to simplify. I'm okay if you leave it like this. The only time that simplifying is useful is if it said something like, where does the denominator equal 0? And if that was the case, or not where does the denominator equal 0, but where is the derivative equal to 0? And then if that were the case, I would say, okay, well now this is 6x cubed minus 6x squared minus 2x cubed all over x minus 1 squared. And so then this would give me 4x cubed minus 6x squared over x minus 1 squared. And if it said, where is the derivative equal to 0, you set this equal to 0 and figure out what x values work in that case. So any questions on the quotient rule? Biggest challenge is just making sure that you keep straight which thing gets subtracted. Product rule, order does not matter. You can flip-flop G and F and you'll still get the same thing. Quotient rule, if you flip-flop them, you'll get the wrong answer. So be careful and be aware with that. So 3.3 I like to split up. So we've done like the first chunk of 3, 3, and then we'll do the next chunk of 3-3 on Monday. And the proofs are in the book. I'll just go ahead and tell y'all. None of the test questions are going to be prove this rule, prove that rule. Like, I'm not going to have you prove the product rule or like the power rule, anything like that. But you need to understand more so why they work, and that it's these either adding zeros or it's coming from, they're all coming from the difference quotient, but I'm never going to explicitly ask you, find this derivative, or not find this derivative, but prove this rule. I still might ask you, what's this derivative using the difference quotient and the derivative rules to check your answer. So don't throw the difference quotient out the window just yet. It still does have uses. So, do y'all have any questions? Do y'all want to do any practice with these? That's kind of why I leave a little bit extra time with this one. If y'all don't have anything to, if y'all don't have any of these to practice right now, make sure you practice these at home. You need to be familiar with these. Again, these rules will be used. I won't say that every rule will pop up every class, but we'll be using a lot of them as the class goes on. So get comfortable with them. Words are hard. Have more practice, and the more you practice, the more familiar you'll become with them, and it'll just be a lot easier to do these as time goes on. And so the first set that's in parentheses, it says do first, second, and I think maybe third derivatives, or it might just be first and second. We're not worrying about second derivatives now. Only worry about the first ones. So if y'all don't have any questions, have a good weekend, and I'll see y'all on Monday.